In the last 40 years, CPU speeds have exploded, but memory speeds have only crawled forward. This divergence created what engineers call the memory wall. Today, a modern processor can perform hundreds of operations in the time it takes to fetch a single piece of data from main memory. When your code isn't optimized for data locality, your CPU isn't actually computing. It is mostly just waiting. It sits idle for hundreds of cycles, stalled on a memory request. This is why a simple change in how you organize your data can result in a 100-fold increase in performance. It isn't that the CPU became faster, it's that it finally had something to do. To understand how to fix this, we have to look at the physical reality of the hardware, the cache hierarchy.
To bridge the gap between lightning-fast logic and sluggish RAM, CPUs use a hierarchy of caches. Think of it like your workspace. The L1 cache is like the tools in your hands, extremely fast but very small. L2 is your desk surface. L3 is the filing cabinet in your office. Main memory, that's a warehouse across town. An L1 access takes about 1 nanosecond. A trip to RAM takes 100 nanoseconds or more. If your data is local, meaning it's already in the L1 or L2 cache, your code flies. If the CPU has to reach all the way to RAM, it's like stopping work for 2 minutes every time you need a pencil. Data locality is the art of ensuring that when the CPU reaches for a tool, it's already in its hands.
When the CPU fetches data, it doesn't just grab the single byte you asked for. It fetches a 64-byte chunk called a cache line. This is based on the principle of spatial locality, the idea that if you need one piece of data, you'll likely need the data right next to it very soon. Imagine buying a single egg, but the store forces you to take the whole carton of 12. If you were planning to make an omelet, that's incredibly efficient. But if you only needed one egg and then you needed a screwdriver, you've wasted space and time. High-performance code organizes data in contiguous blocks, like arrays, so that every cache fetch brings in multiple useful items at once. This maximizes the hit rate of your cache and keeps the pipeline moving.
The biggest enemy of data locality is pointer chasing. Think of a linked list. Each node is a separate object, potentially scattered anywhere in memory. To find the third item, the CPU must fetch the first, read its pointer, fetch the second, read its pointer, and finally fetch the third. Each of these fetches is a potential cache miss. Because the nodes aren't neighbors, the 64-byte cache line the CPU fetched for the first node contains nothing useful for the second. You are forcing the CPU to wait for RAM over and over again. This is why an array of 10,000 integers can be processed significantly faster than a linked list of 10,000 integers, even if the algorithmic complexity, the big O, is exactly the same. Hardware doesn't care about big O, it cares about the cache.
To solve this, we shift from object-oriented thinking to data-oriented design. Instead of thinking about objects that contain everything about one entity, we think about arrays that contain one property for many entities. Imagine a game with 1,000 enemies. In an OO approach, each enemy object has a position, health, and name. If you only want to update positions, you're loading health and names into the cache unnecessarily. In a data-oriented approach, you have one array for all positions. When you update them, the CPU loads a cache line full of positions, processes them, and moves to the next. No wasted space, no wasted time. You are working with the grain of the hardware, not against it.
Let's look at a classic example, summing a 2D matrix. If you iterate row by row, you are reading memory linearly. The CPU's prefetcher sees this pattern and starts grabbing the next cache lines before you even ask for them. It's incredibly fast. But if you swap the loops and iterate column by column, you are jumping across memory with every step. For a large matrix, every single access could be a cache mess. The logic is identical, the result is identical, but the column major version can be 10 to 100 times slower because it forces the CPU to wait for RAM on every single addition. This is the secret of high-performance libraries like NumPy or BLAS. They are built entirely around these cache-friendly access patterns.
To wrap up, remember 3 rules. First, prefer arrays over linked structures. Contiguous memory is your best friend. Second, keep your hot data small. If a structure is used in a tight loop, strip out everything that isn't necessary for that loop. Third, access memory in predictable linear patterns. We often talk about clean code in terms of readability, but clean also applies to how data flows through the hardware. When you respect the physics of the CPU, your code doesn't just run, it screams. Start thinking about your data's layout today, and you'll find performance gains you never thought possible. Thanks for watching.